Tonight we are going to talk about a beam of green light, aimed every clear night at a silent mirror 240,000 miles away, and the uncomfortable truth it has been quietly proving for nearly 20 years. The Apache Point Observatory sits on a ridge in the Sacramento Mountains of southern New Mexico, above the town of Sunspot, in a landscape of ponderosa pine and thin, dry air. The observatory was built for darkness and steadiness, far from the light wash of cities, where the atmosphere above the ridge is calm enough that starlight barely trembles. On most nights, when the moon is up and the clouds are gone, a telescope housed in a white dome turns its mirror toward the lunar surface and sends a pulse of laser light across the gulf between worlds. The pulse is shorter than a human heartbeat, briefer than the blink of an eye, lasting no more than 1/10 of a billionth of a second. It climbs out of the atmosphere, crosses the empty 250,000 miles and strikes a small array of glass prisms left on the moon decades ago by astronauts, who have since grown old or died. A handful of photons, perhaps 1 or 2 out of the trillions that began the journey, reflect straight back along the path they came and return to the telescope that sent them. The round trip takes between 2¼ and 2¾ seconds, depending on where the moon happens to be in its orbit that night. The equipment measures the travel time down to a few trillionths of a second, and from that measurement, the scientists derive a distance. And over the years, one careful night after another, the distance has been growing. The moon is leaving. It recedes from Earth at a rate close to 3.8 centimeters every year, roughly the speed at which a fingernail grows, and it has been doing so for as long as there has been a moon to recede. The retreat is not dramatic. You would not notice it in a lifetime, nor in 100 lifetimes, but it is real, and it is measured, and it has been unfolding in silence for more than 4 billion years. And that slow, patient withdrawal has consequences that reach far beyond the tides. The moon is not simply a companion in the sky. It is a weight on a scale, a hand on a wheel, a governor on a spinning machine. Its gravity reaches across the space between and pulls on the Earth, and in doing so it steadies something fundamental, the angle at which our planet tilts as it turns. That tilt, modest and seemingly unremarkable, is the reason we have seasons. It is the reason ice forms at the poles and melts in summer. It is the architecture beneath monsoons, migrations, harvests, and the long, slow rhythm of glacial ages. And the moon, by its presence and its mass, keeps that tilt from wandering. Without it, the angle would drift. It would swing across a wide and pitiless range, tipping the planet into climatic chaos, the way Mars tips now, helpless and unmoored. The moon holds the axis steady, but the moon is moving away, and so the question we are left with, the question that grows sharper every year, is this: what happens to the tilt when the moon is too far away to hold it? What happens to the seasons? What happens to the ice and the rain and the ancient predictability that made this world a place where life could plan ahead? By the end of tonight, you will understand exactly how the moon steadies the Earth, why that arrangement is temporary, and what a world without it might look like. We will sit with the people who measure the moon's escape 1 photon at a time. We will watch the tilt of the planet govern the distribution of sunlight across its surface. We will see how a spinning world in a gravitational crowd can be tuned like an instrument, and how the moon, by the simple fact of being massive and near, has kept the tuning stable for long enough that forests could grow and animals could learn the meaning of winter. And we will look ahead, across a span of time so long that continents will have rearranged themselves, to the era when the moon's grip loosens and the axis begins to wander and the seasons lose their ceiling. Now, let us begin. Consider for a moment what it takes to measure the distance to another world. The moon is not near. It does not sit just beyond the edge of the atmosphere within convenient reach. It orbits at a mean distance of roughly 384,000 kilometers, far enough that light, which crosses the width of a room in the time it takes to blink, requires more than a second to make the journey. and yet the measurement made at Apache Point is precise to a few millimeters, a distance you could cover with your thumb. The precision is almost incomprehensible. If the Earth were scaled down to the size of a basketball, a few millimeters of error at lunar distance would be narrower than a human hair. The instrument that makes this possible is called a Lunar Laser Ranging Station, and it is, in functional terms, a very patient and very expensive stopwatch. The telescope itself is modest by the standards of modern astronomy, a mere 3.5 meters across, housed in a dome that opens to the sky when conditions allow. The laser is a continuum leopard, a device engineered to produce pulses of light so brief that they are measured in picoseconds and so tightly focused that the beam, even after travelling 250,000 miles, spreads to a footprint only 1 kilometre or 2 wide on the lunar surface. The target is smaller still, an array of corner cube prisms, each one a few centimetres across, designed with a geometry so simple and so elegant that any light entering the prism is reflected back exactly along the path it arrived, no matter the angle. 3 of these arrays were placed on the Moon by Apollo astronauts in 1969, 1971, and 1971. 2 more were delivered by Soviet rovers in the same era. The astronauts who set them down pressed them into the dust, locked them into place, and left them there, and the arrays have been sitting in the lunar silence ever since, waiting for light. Every photon that returns carries information. The time it took to make the round trip is a direct measure of the distance it travelled, and because the speed of light is known to extraordinary precision, the calculation is straightforward, but the Moon does not sit still. It moves in an ellipse, drawing closer and then pulling away again over the course of each month, and so the distance changes from night to night. The orbit itself shifts slowly over time, perturbed by the gravity of the Sun and the shape of Earth's equatorial bulge, and so the ranging station must track not only the Moon's position tonight, but the slow drift of its trajectory across years. The data accumulate in careful layers, one measurement, then another, then 1,000 more, and from those layers a pattern emerges. The Moon is not simply moving around the Earth, it is moving away. The recession is driven by the tides. Twice a day the ocean rises and falls, pulled by the gravity of the Moon, and the moving water drags against the shallow seabeds and coastlines of Earth. That friction is small, but it is continuous, and it extracts energy from the planet's rotation. Earth's spin slows, losing a millisecond or two every century, and the energy does not vanish. It is transferred, through a mechanism as old as gravity itself, into the orbit of the Moon. The Moon climbs higher, it moves faster, and the gap between the two bodies grows. The rate is not constant. It depends on the shape of the ocean basins, the depth of the continental shelves, and the resonances that amplify or dampen the tidal flow. At present, the Moon recedes at about 3.8 centimeters per year, a value measured with such confidence that it has become a reference point in geophysics. But the rate was different in the past, and it will be different in the future, because the continents themselves are moving, and the oceans are reshaping, and the tidal system is alive in ways we are only beginning to map. What does not change is the direction. The Moon has been retreating for as long as it has existed, and it will continue retreating for as long as the tides pull and the Earth turns. The arrangement we live within, the configuration of distances and forces that holds the axis steady, is not a permanent feature of the planet. It is a phase, and we are living in the middle of it. It is worth pausing on what the laser ranging station has revealed about the nature of the Moon's influence, because the distance is not merely a curiosity for astronomers. The strength of the Moon's gravitational pull on Earth diminishes with the square of the distance between them. Move the Moon twice as far away, and the force drops to 1/4 of what it was. Move it farther still, and the force weakens further, and with it, the torque the Moon applies to the spinning Earth. That torque is what steadies the tilt. It is what keeps the axis from drifting into resonance with the slow, patient rearrangement of the orbits of Jupiter and Saturn and the other giant planets, whose gravity tugs on Earth's path around the Sun and indirectly on the orientation of Earth's spin. Without the Moon's presence close and massive, that orientation would become unstable, the tilt would begin to wander, and the climate of the planet, which has remained within a navigable range for hundreds of millions of years, would lose the constraints that have made it survivable. The people who tend the ranging station do not speak about their work in those terms. They are interested, for the most part, in tests of general relativity, in the fine structure of the lunar orbit, in whether the gravitational constant is truly constant. But the data they gather, night after night, are also a record of a departure. The Moon is pulling away, and the thread that ties its motion to the stability of Earth's axis is growing thinner, not quickly, not in a way that will matter to anyone alive today, or to their children, or to 100 generations beyond, but across the kind of time that geology measures, the kind of time in which mountain ranges rise and fall, the Moon's recession will matter more than almost anything else we could name. Move from the ridge in New Mexico then, and the green pulse climbing into the dark, and turn your attention to the consequences of what is being measured. Think about the angle at which the Earth tilts as it orbits the Sun, and what that angle makes possible. The tilt is 23.4 degrees, measured as the angle between Earth's rotational axis and the perpendicular to the plane of its orbit. It is the reason that summer in the northern hemisphere occurs when the North Pole leans toward the Sun, and winter arrives when it leans away. The tilt does not change the distance between Earth and Sun by any amount that matters. The variation in solar distance over the course of a year is far smaller than the difference in heating caused by the angle at which sunlight strikes the surface. When the northern axis tilts toward the Sun, sunlight falls more directly on the northern hemisphere, and the days grow long, and the energy absorbed by the ground and the oceans rises. When the axis tilts away, the same amount of light is spread across a larger area, the Sun climbs lower in the sky, and winter takes hold. It is geometry, not distance, that governs the seasons. The angle is not fixed. It oscillates slowly between 22.1 degrees and 24.5 degrees over a cycle that averages close to 41,000 years. The variation is caused by the gravitational influence of the other planets, which tug on the plane of Earth's orbit and on the orientation of the spin axis, and by the precession of the axis itself, which traces a slow circle in the sky over a period of roughly 26,000 years. These oscillations are well understood. They have been measured in the geologic record, written into the layered sediments of ancient lake beds, and the isotopic composition of deep-sea cores. They are part of the Milankovitch cycles, the set of orbital variations that pace the advance and retreat of ice ages, and they operate within boundaries narrow enough that life has learned to navigate them. The tilt swings back and forth, but it does not swing wild, and the reason it does not is the Moon. Without the Moon, the tilt would not remain within that narrow range. Simulations run by planetary scientists solving the equations of motion for an Earth stripped of its satellite show that the axis would wander across a far wider span. In some of those simulations, the tilt drifts to near zero, leaving the planet with almost no seasons at all, the poles in permanent cold and the equator baking under a sun that never moves far from overhead. In others, the tilt swings to 60 degrees, or 80, or higher, tipping the planet so far that the poles spend half the year in continuous sunlight and the other half in continuous dark. The swings are not regular. They are chaotic, driven by resonances between the precession of the spin axis and the slow drift of the orbital plane, and they occur over timescales of millions of years, fast enough to disrupt any climate pattern that depends on predictability, slow enough that no single generation of organisms would witness the change. But the cumulative effect played out over deep time would be devastating. Mars is the proof. Mars has 2 moons, but they are small, little more than captured asteroids, and their combined mass is negligible compared to Earth's moon. Mars has no stabilizer, and so its axis wanders. The tilt of Mars today is about 25 degrees, close to Earth's, but the geologic record preserved in the Martian polar ice and in the distribution of ancient valley networks suggests that the tilt has varied between near zero and more than 80 degrees over the past few million years. When the tilt is low, the poles are the coldest places on the planet, and the ice caps grow thick and stable. When the tilt is high, the poles receive more sunlight in summer than the equator does. The ice sublimates, and the atmosphere thickens with water vapor and carbon dioxide. The climate of Mars is not stable. It has no baseline to return to. And the reason is that Mars spins alone, without a moon large enough to hold it steady. Earth does not spin alone. The moon is there, pulling on the equatorial bulge, applying a torque that forces the axis to precess rapidly enough that it skips over the dangerous resonances, the frequencies at which small perturbations would grow and the tilt would begin to drift without bound. The moon does not lock the axis in place, it tunes it, the way a hand on a spinning top can steady the wobble without stopping the spin. And it has been doing so for long enough that the predictability of the tilt, the fact that winter follows summer and spring follows winter in a rhythm you can count on, has become a feature of the planet so basic that we rarely think to name it. But it is not a given, it is a gift, and it is a temporary one. Think for a while about the physical mechanism that makes this possible, because the moon's role is not intuitive, and it is easy to misunderstand what is actually being stabilized. Earth spins. It completes one rotation every 24 hours, and it does so around an axis that runs through the North and South poles. But Earth is not a perfect sphere. The centrifugal force from the spin has caused the equator to bulge outward, making the planet an oblate spheroid, wider at the middle than it is from pole to pole. The difference is small, about 21 kilometers, but it is enough. The equatorial bulge is a mass distribution, and it is tilted relative to the plane of Earth's orbit around the Sun, and so the gravity of the Sun and the gravity of the Moon pull on it. The pull does not act uniformly. It is stronger on the side of the bulge that is nearer to the attracting body, and weaker on the far side, and so the net effect is a torque, a twisting force that tries to align the bulge with the orbital plane. If Earth were not spinning, the torque would simply tip the planet over, the way gravity tips a leaning tower. But Earth is spinning, and a spinning object resists being tipped. Instead, the torque causes the spin axis to precess, to trace a slow circle in the sky, like a gyroscope nudged by a hand. The precession is slow. The axis takes roughly 26,000 years to complete one circuit, a period long enough that the stars themselves seem to drift across the celestial sphere, and the pole star changes from age to age. The ancient Egyptians looked to a different star than we do. Our descendants, if they are still watching the sky in 12,000 years, will find the North Pole pointing near the bright star Vega. The precession was first noticed, as far as we know, by the Greek astronomer Hipparchus, around 130 years before the Common Era, who compared his own measurements of star positions to those made by earlier observers and found that the coordinates had shifted. He called it the precession of the equinoxes, because the point in Earth's orbit where day and night are equal in length drifts slowly backward through the calendar, and the phenomenon has been known by that name ever since. But precession is not the whole story. The Moon and the Sun together cause the axis to precess, but the direction the axis points, and the angle at which it tilts, are also influenced by the slow changes in the orbits of the other planets. Jupiter, Saturn and the rest pull on Earth's path around the Sun, causing the orbital plane itself to wobble and tilt over periods of tens of thousands to hundreds of thousands of years. Those changes in the orbital plane feed back into the orientation of the spin axis, and if the frequency of the spin precession happens to match the frequency of one of the orbital variations, the system enters a resonance. The small perturbations add up cycle after cycle, and the tilt begins to grow. It is the same principle that lets you push a child on a swing. If you time the pushes to match the swing's natural period, even a small force can produce a large amplitude. For a planet, the result is not a higher swing, it is a climate that loses its moorings. The Moon prevents this. The torque it applies to Earth's equatorial bulge is strong enough, and the resulting precession rapid enough, that the spin axis sweeps past the dangerous resonances before they can take hold. The axis still wobbles. The tilt still oscillates between 22 and 24.5 degrees. But it does not wander farther because the precession frequency is too high to match the slow drift of the orbital plane. The Moon in effect tunes Earth out of resonance. It acts as a damper, a stabilizer, a timing mechanism that keeps the spin axis moving too quickly to fall into the trap. This is not speculation. The role of the Moon in stabilizing Earth's obliquity was demonstrated in detail by Jacques Lascar and colleagues at the Paris Observatory in the early 1990s, using numerical simulations that track the motion of the planets and the orientation of their spin axes over tens of millions of years. The simulations showed that without the Moon, Earth's obliquity would vary chaotically, swinging across a range of more than 60 degrees and possibly as much as 85. With the Moon, the variations are constrained to less than 3 degrees on either side of the mean. The difference is stark, and the mechanism is robust. The stabilization does not depend on any single unusual property of the Earth-Moon system. It depends only on the mass of the Moon, its distance from Earth, and the torque that distance and mass together produce. Change the distance, and the torque changes. Let the Moon recede far enough, and the precession slows, and eventually, after enough time has passed, the precession frequency drops into the range where resonances become possible, and the axis, which has been steady for billions of years, begins to tip. The Moon is not holding the Earth still. It is holding it in motion, at a tempo fast enough to avoid disaster, and the tempo is slowing. Every year, as the Moon climbs higher, the gravitational coupling between the two bodies weakens, the torque diminishes, the precession slows. The change is imperceptible on human timescales, but it is relentless, and it has a destination. The era of stability is not permanent. It is a window, and we are somewhere in the middle of it, and the Moon is drifting slowly and irrevocably toward the far edge. The question that follows, then, is not whether the Moon stabilizes Earth's axis, it is where the Moon came from, and whether the arrangement was ever anything other than an accident. The answer lies not in the present, but in a catastrophe so remote and so violent that the planet it struck no longer exists, and the planet we live on is, in a literal sense, what remained after the collision. The evidence for this event sits in a vault in Houston, locked behind airlocks and nitrogen-filled cabinets, and it was carried there in aluminum cases by men who walked on another world and returned with pieces of it in their hands. The story begins 4.5 billion years ago, in the early Hadean Eon, when the Sun was young and the solar system was still assembling itself from the disk of gas and dust that had collapsed to form it. The planets were not yet planets in the sense we would recognize. They were protoplanets, bodies that had accreted enough mass to dominate their orbital neighborhoods, but had not yet swept their paths clean. The inner solar system was crowded and collisions were common. Most of these collisions was destructive. A smaller body would strike a larger one, shattering into fragments or merging with the target, and the debris would either reaccrete or be lost. Occasionally, though, a collision would occur between two bodies of comparable size, and the result would be something stranger. The energy released in such an impact is difficult to convey in terms that feel real. The kinetic energy of a Mars-sized object moving at several kilometers per second is enough to vaporize rock, to turn solid mantle into a glowing cloud of silicate vapor that expands into space like a breath in winter air, and the temperatures involved are high enough that the chemistry of the material changes in ways that leave a signature readable billions of years later. This is what happened to Earth. At some point in the first 100 million years after the Sun ignited, a protoplanet roughly the size of Mars, moving in an orbit that brought it close to Earth's path, either drifted into a resonance or was perturbed by another body, and its trajectory shifted. The shift was small, but it was enough. Over the course of thousands of years, the orbits converged and eventually the two bodies met. The impactor has been given a name, though it never had one while it existed. It is called Theia, after the Titan in Greek mythology who was the mother of Selene, the moon. The choice is deliberate and a little melancholy, because Theia did not survive the encounter. Neither, in a sense, did the Earth it struck. The collision was not a glancing blow. Early models of the moon's formation assumed that the impact was oblique, with Theia sideswiping the Earth and shearing off a portion of both bodies' mantles, but more recent simulations, constrained by isotopic measurements of lunar samples, suggest something more direct. Theia struck the Earth almost head-on, at a velocity high enough that both bodies fragmented. The cores of the two protoplanets merged, sinking into the centre of the combined mass under their own gravity, and the mantles were flung outward in a superheated cloud that stretched thousands of kilometres into space. Some of the material fell back to Earth, some escaped entirely, and some of it, perhaps most of it, remained in orbit, a disk of molten droplets and vapour that began to cool and coalesce within hours. The moon formed quickly. The best estimates suggest that it took less than a century for the debris disk to gather itself into a single body, and possibly as little as a day. The process was not gentle. The moon was born hot, possibly molten throughout, and it remained that way for millions of years, cooling slowly in the vacuum of space while the Earth beneath it solidified and began to form a crust. The early moon was not the pale, cratered companion we see now. It was a glowing sphere, bright enough to cast shadows, and it hung in the sky at a distance so close that it would have filled a large portion of the horizon. At the time of its formation, the moon orbited Earth at a distance of somewhere between 15,000 and 25,000 kilometres, roughly 4 Earth radii, compared to its current mean distance of 384,000 kilometres. From the surface of the early Earth, if there had been anyone to see it, the moon would have subtended an angle 30 to 40 times larger than it does today. It would have been a disk, not a point, and the light it reflected from the young sun would have been enough to read by, had there been anything to read. The evidence for all of this is indirect because the event itself left no rocks. The impact melted or vaporized everything it touched, and the Earth's surface has been reworked so many times by plate tectonics and erosion that no trace of the Dean crust remains. But the moon is different. The moon has no plate tectonics, no atmosphere, and almost no internal heat. Its surface is a record of the first billion years of the solar system, and when the Apollo astronauts brought samples of that surface back to Earth, they brought the evidence with them. Between 1969 and 1972, 6 Apollo missions landed on the moon, and the crews of those missions collected a total of 842 pounds of lunar material: rocks, soil, core samples, and dust. The samples were packed in vacuum-sealed containers, flown back to Earth, and delivered to the Lunar Sample Laboratory Facility at NASA's Johnson Space Center in Houston, where they have been stored and studied ever since. The facility is clean, cold, and dry. The samples are kept in nitrogen-filled cabinets to prevent contamination by water vapor or oxygen, and they are handled with tools that have been baked to remove organic residues. Some of the samples have never been opened. They were sealed on the moon, inside containers designed to preserve the vacuum, and they remain sealed today, held in reserve for future scientists with better instruments and new questions. But many of the samples have been analysed, and the results of those analyses are what moved the giant impact hypothesis from speculation to the leading explanation for the moon's origin. The key finding is isotopic. Isotopes are variants of the same element that differ only in the number of neutrons in the nucleus, and because they have the same chemical properties, they do not separate during most geological processes. The ratio of one isotope to another is therefore a fingerprint, a signature of where the material came from and what happened to it. When scientists measured the ratios of oxygen isotopes in lunar rocks, they found that the ratios were nearly identical to those in Earth's mantle. The same was true for other elements. titanium, chromium, tungsten. The Moon and the Earth share an isotopic signature so similar that it implies a common origin, or at least a thorough mixing of material from both parent bodies during the formation event. This rules out most of the alternative theories. If the Moon had formed separately and been captured by Earth's gravity, its isotopic composition would reflect wherever it formed, and the odds of that composition matching Earth's by chance are vanishingly small. If the Moon had condensed from the same disk of material that formed Earth, without an impact, it would have had a different bulk composition, richer in iron, and it does not. The giant impact hypothesis is the only model that explains why the Moon is so similar to Earth in its isotopes, so different in its bulk density, and so large relative to the planet it orbits. No other moon in the solar system is remotely comparable in size to its host, and the reason is that no other moon was born from a collision. The impact did more than create the Moon. It also set the conditions for the stability that would follow. The debris disk from which the Moon formed inherited the angular momentum of the collision, and as the Moon coalesced, that momentum was divided between Earth's rotation and the Moon's orbit. The Earth spun faster, the Moon orbited closer, and the two bodies were gravitationally locked in a configuration that has been slowly unwinding ever since. The early Earth rotated much faster than it does today. The length of a day shortly after the Moon's formation is estimated to have been between 4 and 6 hours, which means the planet completed a full rotation in the time it now takes to eat dinner. The rapid rotation flattened the Earth slightly, producing a pronounced equatorial bulge, and that bulge became the handle by which the Moon's gravity could apply torque. The Moon pulled on the bulge, and the bulge, which was carried ahead of the Moon by Earth's faster rotation, pulled back on the Moon, accelerating it in its orbit. The result was a transfer of energy. Earth's rotation slowed, losing angular momentum, and the Moon's orbit expanded, gaining it. This is the process called tidal friction, and it has been operating continuously for more than 4 billion years. The tides themselves in the early Earth-Moon system were extraordinary. Tidal forces scale with the inverse cube of the distance, which means that when the Moon was 4 times closer, the tides were 64 times stronger. If the early Earth had oceans, and the evidence suggests that it acquired them relatively early in its history, those oceans would have risen and fallen by hundreds of meters twice a day, scouring the coastlines and dissipating enormous amounts of energy as heat. Even the solid body of the Earth experienced tides, bulging and flexing as the Moon passed overhead, and the friction generated by that flexing contributed to the heating of the interior. The Moon receded quickly at first. The rate of recession is not constant. It depends on the configuration of the continents and ocean basins, which control how efficiently tidal energy is dissipated, and those configurations have changed over time. But the overall trend is clear. The Moon has been moving away from Earth since the moment it formed, and the recession continues today, measured to millimeter precision by the green laser pulses that travel from a station in the mountains of New Mexico to the retroreflectors left on the lunar surface by the Apollo crews. The current rate is 3.8 centimeters per year, which is roughly the speed at which a fingernail grows. It is slow, but it is not Tinggi-able, and over billions of years it adds up. The irony is this: the same process that pushed the Moon outward and slowed Earth's rotation also established the conditions for the stability we now enjoy. As the Moon receded and the Earth's spin slowed, the length of the day increased, approaching the familiar 24 hours, and the tides became gentler, and the gravitational coupling between the two bodies settled into a configuration that was strong enough to stabilize the axis, but not so strong as to lock the planet's rotation entirely. The Moon gave Earth its rhythm: the day, the month, the tides, and the constancy of the seasons. But the gift was never permanent. It was a phase, a window in time, and the window is closing. The Moon is leaving, and as it leaves, the leverage it exerts on Earth's axis weakens. The precession slows. The resonances that the Moon has kept at bay for billions of years come closer. The system is stable now, but stability in this context is not an equilibrium. It is a temporary balance, maintained by a force that is itself diminishing. The moon is not holding the Earth still. It is holding it in motion, and the motion is slowing, and eventually, on timescales measured in tens or hundreds of millions of years, the motion will slow enough that the resonances can take hold, and the axis will begin to wander. The catastrophe that built the stabilizer occurred 4.5 billion years ago, and it was not a catastrophe in the sense of something that destroyed a thriving world. It was a catastrophe in the sense of something that destroyed one world and built another in its place. The Earth that existed before the impact is gone. The Earth we live on is the one that remained after Theia struck, and the moon that steadies our axis is the child of that collision, born in fire and still climbing slowly away from us. The arrangement is not a design, it is an accident. But it is an accident that made everything else possible, and for as long as it lasts, it is the reason the planet beneath us turns at a tilt that does not wander, and the seasons return, and the climate, for all its variability, remains within bounds that life can navigate. Consider for a moment the question of how we know any of this. The models are elegant, and the simulations convincing, but the recession of the moon and the lengthening of the day are not conjectures pulled from theory alone. They are facts written into the Earth itself, recorded in stone by processes so patient and so repetitive that they function as clocks, and those clocks can be read if you know how to look. There are places on this planet where the tides have been writing their history for hundreds of millions of years. The evidence is subtle, and for a long time it went unnoticed, because it takes a particular kind of attention to see a rhythm preserved in rock. But once you learn to recognize it, the story becomes unmistakable. The moon was closer, the day was shorter, the tides were stronger, and all of it is there, in the stone, waiting. One of the clearest records lies in the Flinders Ranges of South Australia, in a formation called the Elatina. It is a sequence of reddish-brown siltstones and sandstones, about 10 meters thick, exposed in a place called Pichirichi Pass, and it dates to roughly 620 million years ago, in the late Neoproterozoic, during a period called the Cryogenian. The name is fitting. The Cryogenian was a time of extreme glaciation, possibly the most extreme in Earth's history, when ice may have extended all the way to the equator, and the planet entered a state sometimes referred to as Snowball Earth. The Elatina Formation was deposited during that interval, in a shallow marine environment, and the sediments that make it up were laid down by tides. The rocks are layered, and the layers are thin, and they vary in thickness in a way that is not random. The variation is rhythmic. Some layers are thicker, some thinner, and the pattern repeats with a regularity that reflects the influence of the tides on the rate at which sediment was deposited. When the tides were strong, more sediment was moved and laid down. When the tides were weaker, less sediment accumulated. The result is a stack of laminae, each one representing a single tidal cycle, and the thickness of each lamina is a record of the strength of the tide that deposited it. The tides themselves are not simple. There are daily tides driven by the rotation of the Earth beneath the tidal bulge raised by the moon. There are monthly tides, driven by the changing distance between the Earth and the moon, as the moon moves through its elliptical orbit, and by the changing alignment of the sun, Earth and moon, as the moon passes through its phases. There are yearly tides, modulated by the changing distance between the Earth and the sun, as the Earth moves through its own elliptical orbit. All of these cycles are superimposed, and all of them leave their mark in the sediment, and the Elatina Formation preserves them all. Dr. George Williams, a geologist formerly of the University of Adelaide, pioneered the analysis of these tidal rhythmites. The work is painstaking. You count the laminae, you measure their thickness, you look for the nested cycles, the places where the pattern of thick and thin layers repeats at intervals that correspond to known tidal periods, and from those measurements, you can reconstruct the parameters of the Earth-Moon system as it existed 620 million years ago. The analysis of the Elatina rhythmites reveals that a day, at that time, lasted 21.9 hours, give or take about 24 minutes. A year, which is determined by Earth's orbit around the Sun and has not changed significantly over this span of time, contained 400 days, give or take 7. There were 13.1 synodic months per year, which is to say 13 full cycles of the moon's phases from new moon to new moon. And the moon itself orbited at a distance that was roughly 96.5% of its current average distance, which places it about 13,000 kilometers closer than it is today. From these figures, you can calculate the rate at which the moon has been receding over the intervening 620 million years. The average works out to just over 2 centimeters per year. That is slower than the current rate of 3.8 centimeters per year, and the difference is significant because it tells you that the recession is not constant. The rate depends on how efficiently the Earth's oceans dissipate tidal energy, and that efficiency depends on the shape and size and arrangement of the ocean basins, which have changed as the continents have drifted and the seafloor has spread and the coastlines have shifted. The current rate is anomalously high, and the reason has to do with resonance. The North Atlantic Ocean, in its present configuration, has a natural oscillation frequency that nearly matches the frequency of the tides. When that happens, the tides are amplified and more energy is dissipated and the moon recedes faster. It is a temporary condition in the sense that the continents will continue to move and the resonance will eventually shift. But on human timescales it is effectively permanent, and on geological timescales it is a blink. The long-term average recession rate, measured over hundreds of millions of years, is lower than what we see today, and that is what the Elatina Formation shows. The details matter, but the broader picture is simple. The moon was closer, the Earth turned faster, the day was shorter and the month was shorter, and the tides were stronger. And all of it is recorded in stone, not as a theory or a model, but as a fact, layered and countable and checkable. The recession is not a speculative future plot. It is a measurable process, written into the planet's history, and the history extends all the way back to the beginning. There are other formations like Elatina scattered around the world, preserving tidal rhythms from different eras. Each one is a clock, each one can be read, and together they tell the same story. The moon has been leaving for as long as there has been a moon, and the Earth has been slowing for as long as there has been an Earth with a moon to slow it. The process is relentless, and it is quiet, and it is as fundamental to the planet's history as the movement of the continents or the cycling of the ice ages. The significance of this for the stability of the axis is straightforward. The gravitational coupling between the Earth and the moon is what keeps the precession of the axis steady and keeps the resonances at bay. As the moon recedes, the coupling weakens. As the coupling weakens, the precession slows. And as the precession slows, the system drifts closer to the conditions under which the resonances can take hold. The tidal rhythmites tell you that this has been happening for hundreds of millions of years, and they tell you that it will continue to happen for hundreds of millions of years more, and they tell you that the stability we enjoy now is not a permanent feature of the planet. It is a phase, and the phase is ending slowly but measurably at the speed of a fingernail growing. Turn now to Mars, and the warning becomes vivid. Mars is the nearest planet to Earth in terms of size and structure and distance from the Sun, and for much of its early history it may have resembled Earth in other ways as well. There is overwhelming evidence that Mars once had liquid water on its surface, carved into vast networks of valleys and pooled in ancient lake beds and possibly gathered into seas, or even an ocean that covered much of the northern hemisphere. The climate that allowed for liquid water is long gone. Mars today is cold and dry, its atmosphere thin, its surface scoured by dust storms and radiation. But the evidence of a warmer, wetter past is undeniable, and one of the reasons the climate changed so drastically has to do with the wandering of its axis. Mars has 2 moons, Phobos and Deimos, but they are tiny, irregular chunks of rock, more like captured asteroids than proper moons, and they exert almost no gravitational influence on the planet's axial tilt. Without a large stabilizing moon, Mars is subject to chaotic perturbations from the gravitational nudges of the other planets. primarily Jupiter, Saturn, Venus, and Earth itself. Those nudges are small, but they accumulate, and over millions of years they push and pull on Mars's orbit and on its spin axis, and the result is that the obliquity of Mars, its axial tilt, swings wildly. Numerical simulations, many of them associated with the celestial mechanics work of Jacques Lascar and his colleagues at the Paris Observatory, show that Mars's obliquity can range from nearly 0 degrees to more than 80 degrees over timescales of millions to tens of millions of years. The current tilt is about 25 degrees, which is close to Earth's, but that is a snapshot, a moment in a chaotic trajectory that has no equilibrium. At high obliquity, the poles receive more direct sunlight during summer than the equator does, and the seasonal swings become extreme. Ice sublimates from the polar caps and is redeposited at mid-latitudes. The climate zones shift, the planet transforms. The evidence for this is written into Mars's polar ice caps, which are thick stacks of layered deposits, alternating bands of dust and water ice, each layer a record of a different climatic period. The layers are visible in orbital images and have been probed by radar instruments on spacecraft like the Mars Reconnaissance Orbiter. They show that Mars has experienced multiple ice ages, periods when ice accumulated in different places under different conditions, and the pattern of accumulation is consistent with the kind of axial wandering that the simulations predict. Mars is a planet whose climate is governed not just by its distance from the Sun or the composition of its atmosphere, but by the angle at which it tilts, and that angle is unstable. The loss of Mars's atmosphere is tied to this as well. When the obliquity is high, the poles warm and ice sublimates, and the atmospheric pressure increases. When the obliquity drops, the opposite happens. The cycling between high and low obliquity may have contributed to the gradual stripping of the atmosphere by solar wind, because a thicker atmosphere is more vulnerable to being blown away when the planet's magnetic field, which Mars lost early in its history, is not there to shield it. The axial instability, in other words, is not just a curiosity. It is one of the mechanisms by which Mars became uninhabitable. Mars is a demonstration, a nearby case study in what happens to a planet when its axis is free to wander. It is not that Mars lacks seasons. It is that the seasons are unpredictable on long timescales, and the climate zones shift, and the conditions that might allow for stable liquid water on the surface appear and disappear over intervals too long for any ecosystem to adapt continuously. Mars had water, and it had a thicker atmosphere, and it may have had conditions suitable for life, but it could not hold on to any of those things, in part because it could not hold its axis still. Earth, by contrast, has remained stable. The tilt oscillates within a narrow range, 22.1 to 24.5 degrees, over a cycle of roughly 41,000 years, but it does not wander outside that range. The reason is the Moon. The Moon's gravitational torque on Earth's equatorial bulge drives the precession of the axis at a steady rate, about once every 26,000 years, and that steady precession keeps the system away from the resonances that would allow the obliquity to swing chaotically. The Moon is not holding the Earth still, it is holding it in a particular kind of motion, a motion that is regular enough to be predictable, and the predictability is what matters. But the motion is not isolated. Earth's orbit is not a perfect ellipse, fixed in space. It is subject to continuous gravitational perturbations from the other planets, primarily Jupiter and Saturn, but also Venus and Mars. Those perturbations change the shape of the orbit, its eccentricity, and the orientation of the orbit, the direction in which its long axis points. The changes are slow, periodic, and they occur on timescales of tens of thousands to millions of years. The orbit becomes more elliptical, then less elliptical, then more elliptical again. The orientation of the orbit precesses, rotating slowly in space. All of this is well understood and has been modelled in detail. One of the most regular of these cycles is driven by the gravitational interaction between Jupiter and Venus. It repeats every 405,000 years, and it has remained consistent for at least 215 million years, possibly longer. The cycle modulates Earth's orbital eccentricity, the degree to which the orbit deviates from a circle, and that in turn modulates the amount of solar radiation the Earth receives at different times of the year. This is one of the factors that drives the ice ages, part of the set of orbital cycles known as Milankovitch cycles. The point is that Earth's orbit is not static. It is dynamic, continuously perturbed, and the perturbations interact with the precession of the axis in ways that can amplify or dampen the effects of the axial tilt on climate. The critical issue is resonance. A secular resonance occurs when the precession frequency of a planet's spin axis matches the precession frequency of its orbital orientation. When that happens, the small periodic nudges from the other planets can accumulate constructively, and the axial tilt can begin to swing. This is what happens to Mars. The precession of Mars's spin axis is slow, because Mars has no large moon to drive it, and that slow precession wanders into and out of resonance with the precession of its orbit and the orbital precession of the other planets. When the resonance occurs, the obliquity swings. When it does not, the obliquity is more stable, but the system is always vulnerable. Earth avoids this fate because the Moon drives the precession of Earth's axis at a frequency that is much faster than the precession frequencies associated with the orbital perturbations. The lunar-driven precession, once every 26,000 years, is fast enough that it stays well clear of the strongest resonances. The result is that the small periodic nudges from Jupiter and Venus and the others never get the chance to accumulate. They are averaged out by the faster precession, and the axial tilt remains constrained. But the precession is slowing. As the Moon recedes, the gravitational torque it exerts on Earth's equatorial bulge diminishes, and the precession rate drops. The process is slow, measured in fractions of a second per century, but it is steady, and over millions of years it will bring the precession frequency down into the range where the resonances live. When that happens, the axis will no longer be protected. The obliquity will begin to wander, and the climate will begin to swing between extremes, and the predictability that has characterized Earth's climate for billions of years will break down. This is not speculation. The mathematics of orbital mechanics allows for detailed numerical simulations of the long-term evolution of the solar system, and those simulations, pioneered by Jacques Lascar and others in the early 1990s, show that without the Moon, Earth's obliquity would be chaotic. The tilt could swing anywhere from 0 degrees to 85 degrees or more on timescales of millions of years. With the Moon, the tilt is stable, but the stability depends on the strength of the lunar torque, and the torque is weakening. The simulations show that the system will remain stable for tens of millions of years, possibly longer, but not indefinitely. Eventually the precession will slow enough that the resonances will take hold and the axis will begin to drift. The exact timing is uncertain because it depends on factors that are difficult to model with precision over such long timescales. The configuration of the continents will change, the distribution of ice and water will change, the tidal dissipation rate will change. All of these affect the rate at which the Moon recedes and the rate at which the precession slows. But the overall trend is clear. The Moon is leaving, and as it leaves, the corridor of stability narrows. Earth's axial stability is not a permanent feature. It is a temporary arrangement, maintained by a force that is itself diminishing, and the arrangement will not last forever. The resonances are already there, woven into the fabric of the solar system's orbital dynamics. They have always been there. The Moon has kept Earth away from them for billions of years, but the Moon is not a wall. It is a guide, a force that keeps the system in motion along a particular path, and the path is stable only as long as the motion is fast enough. The tension is this. Stability in this context is not stillness. It is motion through a landscape of resonances, and the motion is slowing, and the landscape is fixed, and eventually the slowing motion will bring the system into the resonance zone. When that happens, the axis will no longer be constrained. The tilt will begin to wander, and the seasons, which have been predictable for as long as complex life has existed on this planet, will become unpredictable. The climate will swing between extremes. Ice will advance and retreat in patterns that no longer follow a regular cycle, and the stability that made a predictable planet, a planet on which life could plan for the future, will be gone. Mars shows what that looks like. Mars is the unmoored planet, the one that lost its stabilizer, if it ever had one, and its climate history is written in layers of ice and dust, a record of a world that swings between states, unable to settle. Earth has avoided that fate for 4.5 billion years, but the avoidance is not guaranteed. It is the result of a gravitational coupling that is weakening year by year, centimetre by centimetre, at the speed of a growing fingernail measured by green laser light reflected from mirrors left on the surface of a receding moon. The question, then, is what would have happened if the moon had never been there at all? Not the world we have now, stripped of its companion, but a world that formed alone from the beginning, with no giant impact, no debris disk, no accidental stabilizer locking the axis into a narrow corridor. A world spinning under the same gravitational pressures from Jupiter and Saturn and the other planets, but without the lunar torque to hold the precession frequency high, without the gravitational hand keeping the resonances at bay. This is not an idle thought experiment. It is a question that can be answered, at least in outline, by numerical simulation, and the answer tells us something essential about the planet we live on. It tells us how rare the conditions are, and how fragile, and how much of what we take for granted about Earth's climate is the result of an arrangement that could easily have been otherwise. In the early 1990s, a small group of researchers at the Bureau des Longitudes in Paris began constructing long-term integrations of the solar system's orbital evolution. The Bureau itself is an old institution, founded in the 18th century to calculate ephemerides for navigation, and by the late 20th century it had become a centre for celestial mechanics, the patient arithmetic of predicting where planets will be millions of years from now. The work requires integrating the equations of motion for all the major bodies in the solar system, forward through time, accounting for every gravitational tug and every orbital perturbation, and it is computationally expensive. But by the early 90s the computers were fast enough and the numerical methods were sophisticated enough that it became possible to run these integrations out to timescales of tens of millions of years. The results were unsettling. The orbits were not as stable as earlier, shorter integrations had suggested. Small perturbations could grow over time, driven by resonances, and the long-term behaviour of the system was more chaotic than anyone had expected. Jacques Lascar, working with François Joutel and Philippe Robutel, turned the method toward a specific question. What would happen to Earth's axial tilt if the moon were not there? They began by constructing a model of the Earth-Moon system as it exists, with all the orbital parameters and the measured recession rate, and the known strength of the lunar torque. They let the simulation run forward, and the obliquity remained stable, oscillating in its familiar range of 22 to 24.5 degrees as expected. Then they removed the moon from the calculation. They kept everything else the same: the Earth's rotation rate, its orbit, the presence of Jupiter and Saturn and the other perturbing bodies, but they took away the lunar torque, the stabilizing force that keeps the precession fast, and they ran the simulation again. The results were published in Nature in February of 1993, and they showed something stark. Without the moon, Earth's obliquity did not remain in a narrow range. It wandered. Over the course of millions of years, it drifted upward and downward through a much wider span, sometimes reaching values near zero, sometimes climbing past 60 degrees, sometimes higher still. The precise range depended on the initial conditions and honest assumptions about Earth's primordial rotation rate and the rate of tidal dissipation, but the overall pattern was robust. In many of the runs, the obliquity could diffuse anywhere from near zero to 85 degrees or more, swinging chaotically through a space of possible tilts, because the resonances were no longer being avoided. The precession frequency, without the moon, was much slower, and the slow precession brought the system into resonance with the precession of the orbital plane, and once in resonance, the perturbations from the other planets could drive large changes in the tilt. The axis was no longer locked. It was free to wander, and it did wander, across timescales of millions of years, in patterns that showed no regularity, no predictable cycle. The tilt at any given moment depended on the history of perturbation stretching back millions of years, and small differences in initial conditions led to large differences in outcome. It was, in the technical sense, chaotic. The finding was not universally accepted at first, and subsequent work, using more sophisticated integrators and longer timescales, has refined the picture. Some later simulations have suggested that even without the Moon, if Earth's rotation were fast enough, the obliquity might remain somewhat constrained, wandering perhaps between 20 and 25 degrees rather than across the full chaotic range. The details depend on factors that are difficult to pin down over such long time scales. The precise rate at which tidal friction slows the rotation, the way continents shift and alter the tidal dissipation, the feedback between obliquity changes and the climate system itself, but the larger point has held up. A moonless Earth would be much less predictably tilted than the Earth we have. The axis would be vulnerable to resonances that, in our world, are kept at arm's length by the lunar torque. The tilt would not be fixed, and it would not oscillate in a narrow, regular band. It would wander, and the wandering would be large enough and unpredictable enough to remake the planet's climate repeatedly over geological time. The question is no longer whether this would happen, but how severe the swings would be, and what those swings would mean for the surface of the planet. Turn the numbers into climate, and the implications unfold slowly, layer by layer. Start with the geometry. Axial tilt determines how sunlight is distributed across the surface of a planet over the course of a year. At 23.5 degrees, the tilt we have now, the sun's rays strike the equator nearly directly year-round, and the poles receive their sunlight at a steep angle, which spreads the energy over a larger area and weakens it. The difference between summer and winter at any given latitude is the result of the tilt. In summer, your hemisphere is tilted toward the sun climbs higher in the sky, the days are longer, and more energy arrives. In winter, the opposite. The poles experience the most extreme version of this, 6 months of daylight, 6 months of night, with the sun never climbing far above the horizon even at midsummer. This is the seasonal pattern that has governed Earth's climate for as long as there has been an atmosphere to respond to it. Now imagine the tilt near zero. The sun shines almost directly on the equator all year, and the poles receive almost no direct sunlight at any time. There are no seasons in the familiar sense. The equator is hot, the poles are cold, and the gradient between them is steep and permanent. Sunlight that currently reaches the high latitudes in summer, melting snow, warming the oceans, driving the atmospheric circulation that redistributes heat, no longer arrives. The polar regions, starved of summer sunlight, cool. Snow that falls in winter does not melt. Ice sheets begin to grow, and once they grow, they reflect more sunlight back into space, which cools the surface further, which allows the ice to grow more still. This is the ice albedo feedback, one of the most powerful amplifiers in the climate system, and at very low obliquity it runs unchecked. The ice advances year after year, century after century, spreading outward from the poles toward the mid-latitudes, and the planet enters a state that is colder, on average, than anything it has experienced in the last billion years. The equator remains warm, possibly hot enough to remain ice-free, but the tropics narrow, the habitable zones shrink, and the circulation of the oceans and atmosphere is reshaped around a steeper temperature gradient. How far the ice advances depends on many factors: the concentration of greenhouse gases, the configuration of the continents, the brightness of the sun, which has been slowly increasing over geological time, but the forcing is clear. Low obliquity favours ice. Now imagine the opposite. The tilt climbs to 60 degrees, 70, 85. At 85 degrees, the planet is spinning nearly on its side like Uranus, and the geometry of sunlight is inverted. The poles, for half the year, are tilted almost directly toward the sun. they receive intense, continuous illumination, more energy per square meter than the equator, because the sun never sets and the rays arrive nearly straight down. The other pole for that same half year is tilted away, locked in continuous darkness. Then the planet moves around its orbit, and the situation reverses. The pole that was in daylight falls into night, and the pole that was in night swings into daylight. The equator, by contrast, experiences something closer to perpetual twilight, with the sun skimming the horizon twice a day but never climbing high. The seasonal contrast is no longer between summer and winter at a given latitude. It is between the pole that is currently illuminated and the pole that is not. The summer pole bakes. Ice that has accumulated there over millennia melts rapidly. The surface, freed of its reflective snow cover, darkens and absorbs more heat, which accelerates the melting further. Meltwater runs into the oceans, raising sea levels. The atmospheric circulation, which on present-day Earth is organised around the equator-to-pole temperature gradient, reorganises around the pole-to-pole gradient. Winds and ocean currents shift, rainfall patterns shift, deserts move, forests die and are replaced by grasslands or by tundra or by nothing at all, depending on the new configuration of moisture and temperature. Then, 6 months later, the illuminated pole falls into darkness, and the whole system begins to reverse. The pole that was melting begins to freeze, the pole that was frozen begins to melt, and the climate, trying to respond to these enormous rapid changes in energy input, swings between states, never settling, never reaching equilibrium, because the forcing itself is oscillating on a timescale that is short compared to the response time of ice sheets and ocean circulation. The planet is not in a permanent hot state or a permanent cold state. It is in a state of continuous violent reorganization. The point is not that high obliquity makes the planet uninhabitable, or that low obliquity does. Life is resilient, and it adapts, and there are organisms on Earth today that survive in environments far harsher than anything a change in axial tilt could produce. The point is that the changes are unpredictable, and they are large, and they happen on timescales that are short compared to the timescales on which evolution usually operates, but long compared to the lifespan of any individual organism or any single species' ecological niche. If the obliquity swings from 10 degrees to 70 degrees over the course of 5 million years, the climate does not transition smoothly. It reorganizes repeatedly in fits and starts, each time the tilt crosses a threshold where some feedback kicks in or shuts off. The ice albedo feedback is one. The behavior of atmospheric water vapor is another. Warmer air holds more water vapor, which is itself a greenhouse gas which warms the planet further, which allows the air to hold even more water vapor. The response of vegetation is another. Forests are darker than grasslands, which are darker than deserts, and each transition changes the amount of sunlight reflected back into space, which changes the temperature, which changes what can grow. The ocean circulation is another. The thermohaline circulation, the slow overturning driven by differences in temperature and salinity, can shut down or reorganize when the surface temperature distribution changes, and when it does, it alters the distribution of heat around the planet, which can trigger abrupt regional climate shifts. All of these feedbacks are always present, but on present-day Earth they operate within a relatively narrow envelope of forcing, because the obliquity itself is constrained. Remove that constraint, let the obliquity wander, and the feedbacks are no longer operating around a stable mean. They are amplifying changes that are themselves large and chaotic, and the result is a climate system that is constantly being pushed out of equilibrium, over and over, with no predictable return to any particular state. This is the condition that Mars experiences. Mars has 2 small moons, Phobos and Deimos, but they are far too small to exert any meaningful torque on its spin axis. Mars is effectively moonless, in the sense that matter's here, and its obliquity has wandered over a large range. The current tilt is about 25 degrees, close to Earth's, but studies of Martian ice deposits and layered polar sediments suggest that the obliquity has swung between 0 and at least 45 degrees, and possibly much higher, over the last few million years. When the tilt is high, the summer poles receive intense sunlight, and carbon dioxide ice sublimes from the polar caps into the atmosphere, thickening it temporarily, which warms the planet slightly, which allows more ice to sublime, which thickens the atmosphere further. When the tilt is low, the reverse happens. The poles are cold year-round, carbon dioxide condenses out of the atmosphere and freezes onto the surface, and the atmospheric pressure drops. The climate swings between states that are slightly less cold and states that are much colder, and there is no regularity to the swings, no cycle that a Martian organism could adapt to over evolutionary time, because the obliquity itself is chaotic. Mars is a demonstration of what happens when a terrestrial planet loses, or never has, the stabilizing influence of a large moon. It becomes a world where the climate is governed not only by the slow, predictable changes in orbital parameters, the eccentricity, the precession of the perihelion, but also by the chaotic, unpredictable changes in the axis itself, and the chaos makes it difficult for any climate state to persist long enough to become stable, long enough for life, if it exists, to adapt in a way that is more than provisional. Earth has avoided this so far because the moon has kept the precession fast, and the fast precession has kept the system out of resonance. But the moon is receding, the torque is weakening, and the precession is slowing, and the question is no longer whether Earth will eventually enter the chaotic regime, but when and how severe the first swings will be, and whether the timescale is short enough to matter to anything we care about. The simulation suggests that the stability will persist for tens of millions of years, possibly a few 100 million, depending on how quickly the precession slows and how the tidal dissipation rate changes as the continents drift and the ocean basins reshape. But the uncertainty is large, because the models are sensitive to parameters that are themselves uncertain, and because the system is chaotic, which means that small differences in initial conditions can lead to large differences in outcome. What is certain is that the arrangement we have now, the narrow range of obliquity, the predictable seasons, the climate that oscillates around a stable mean, is not a permanent feature of the planet. It is a feature of this particular moment in Earth's history, a moment when the moon is close enough to stabilize the axis but far enough that the tides are not catastrophically strong. A moment that sits in the middle of a much longer trajectory from the moon's formation to its eventual departure. The stability is real, but it is conditional, and the condition is a force that is weakening at a rate of 3.8 centimeters per year. The climate system does not care about human timescales, and the loss of axial stability is not something that will happen in our lifetimes, or in the lifetimes of our descendants for thousands of generations. But it is something that will happen, and it is already beginning, in the sense that the precession is slowing, and the corridor of stability is narrowing, and the resonances that will eventually destabilize the axis are already there, waiting, embedded in the orbital dynamics of the solar system. The planet we live on is stable because of a contingent arrangement of gravity, and the arrangement is temporary, and the awareness of its temporariness is part of the larger awareness that the conditions that allowed complex life to evolve on Earth, the stable climate, the predictable seasons, the long stretches of geological time during which the environment changed slowly enough that evolution could keep pace, are not guarantees. They are the result of a specific history, a specific set of initial conditions, and a specific accident 4.5 billion years ago that gave Earth a companion large enough to hold the axis steady. Without that accident, Earth might have been like Mars, a world that swings between climates, unable to settle, its habitability undermined not by any single catastrophe, but by the chronic unpredictability of its axial tilt. We live on a planet that has been spared that fate, but the reprieve is not permanent. The moon is leaving, the stability is eroding, and the chaotic regime is not a distant, abstract possibility. It is the default state, the state that every terrestrial planet falls into unless something holds it out, and the thing that has been holding Earth out is weakening. Somewhere, millions of years from now, the axis will begin to wander, and the seasons will begin to swing, and the climate will lose the predictability that has characterized it for billions of years. And when that happens, the history of Earth's climate will have entered a new chapter, one defined not by the slow, cyclical variations we have come to understand, but by the chaotic, unpredictable swings that characterize a world without a moon. Consider for a moment the shape of Earth's climate record as it has actually unfolded, not in simulation but in ice and sediment and stone. The planet has not been climatically still, even with the moon holding the axis in place. It has lurched through glaciations and warmings, through epochs when ice sheets crawled south to cover continents, and epochs when forests grew near the poles. The climate has shifted, sometimes abruptly, and the changes have left their mark in layers that can be read like a chronicle of instability. Yet the instability has been bounded, constrained by cycles that repeat with enough regularity that they can be predicted, and the predictability is what distinguishes Earth from Mars, even when Earth is in the grip of an ice age. These cycles themselves are ancient knowledge now, encoded in the geometry of the planet's motion, and they were decoded over the course of the 20th century by researchers who realized that the ice ages were not random convulsions, but responses to changes in the way sunlight fell on the surface, changes driven by slow variations in Earth's orbit and the orientation of its spin. The theory that emerged from that realization is one of the great achievements of planetary science, and it is also a reminder that lunar stabilization does not mean climatic stillness. It means that the variations are bounded, that the swings are constrained, and that the system oscillates around a mean rather than spiraling into chaos. The man who first attempted to calculate the effect of orbital variations on climate was a Serbian mathematician named Milutin Milankovic, and he spent the better part of 3 decades, beginning around 1911, working through the problem with the tools he had: pen and paper, tables of astronomical data, and an extraordinary capacity for sustained arithmetic. He was not the first to propose that changes in Earth's orbit might influence climate, but he was the first to attempt a quantitative model, and the result of his work was a set of curves showing how the distribution of sunlight across the planet's surface had varied over hundreds of thousands of years. The curves were published in the 1920s and 30s, and they were largely ignored for decades, in part because the paleoclimate data needed to test them did not yet exist, and in part because the theory seemed too elegant, too geometric, to account for the messy complexity of the real climate system. It was not until the 1970s, when cores drilled from the ocean floor and the Antarctic ice sheet began to yield high-resolution records of past temperatures, that Milankovic's calculations were vindicated. The data showed that the ice ages had come and gone in rhythm with the orbital cycles he had predicted, and the match was close enough that the cycles were given his name. There are 3 of them, and they arise from the fact that Earth's orbit is not fixed but evolves over time under the gravitational influence of the other planets. The first is eccentricity, the cycle by which the shape of Earth's orbit shifts between nearly circular and slightly more elliptical over a period of roughly 100,000 years. When the orbit is more elliptical, the distance between Earth and the Sun varies more over the course of a year, and the contrast between the seasons becomes more pronounced in one hemisphere and less pronounced in the other, depending on where in the orbit the planet is tilted toward or away from the Sun. The second cycle is obliquity, the slow oscillation of Earth's axial tilt between 22.1 degrees and 24.5 degrees over a period of about 41,000 years. When the tilt is greater, the seasons are more extreme. When it is smaller, they are milder. The third cycle is precession, the wobble of Earth's axis over a period of roughly 23,000 years, which changes the timing of the seasons relative to the planet's position in its orbit. Together, these cycles modulate the amount and distribution of sunlight reaching the surface, and the modulation is enough to tip the climate system into and out of glacial states, provided the system is already close to a threshold. The cycles do not create ice ages by themselves. They pace them, acting as a kind of metronome that sets the rhythm of glaciation and deglaciation. The evidence for this pacing comes from many sources, but the most direct is the record preserved in deep-sea sediment cores and ice cores drilled from the Antarctic ice sheet. The sediments contain the shells of microscopic organisms that lived in the ocean, and the isotopic composition of the oxygen in those shells varies with the temperature of the water and the amount of ice locked up on land. By analysing the isotopes layer by layer, researchers can reconstruct a timeline of glacial and interglacial periods stretching back millions of years, and the timeline shows a clear pattern. The ice ages have come and gone in cycles whose periods match the Milankovitch cycles with remarkable precision. The match was made quantitatively rigorous in 1976 when a team of researchers published a paper in the journal Science with the title Variations in the Earth's Orbit, Pacemaker of the Ice Ages. The paper presented an analysis of sediment cores from the Indian Ocean, and it showed that the dominant periods in the climate record corresponded almost exactly to the periods of the orbital cycles, with the strongest signal at 100,000 years matching the eccentricity cycle, and secondary signals at 41,000 and 23,000 years matching obliquity and precession. The correspondence was so tight that the paper effectively settled the question of whether the Milankovitch cycles were real drivers of climate change. They were, and the framework they provided became the foundation for understanding the Pleistocene, the epoch of repeated glaciations that began about 2.6 million years ago and that ended, or at least paused, roughly 12,000 years ago. The ice cores tell the same story, but with finer detail and a longer reach. The cores drilled from the East Antarctic ice sheet at sites called Vostok and later Epica extend back more than 800,000 years, and they preserve bubbles of ancient air trapped at the time the snow fell and compacted into ice. By measuring the composition of the air and the isotopes in the ice itself, researchers can reconstruct both the temperature and the atmospheric concentration of greenhouse gases at the time each layer formed, and the resulting record is one of the most important datasets in all of climate science. It shows a world that has oscillated between warm interglacial periods, much like the present, and cold glacial periods, during which temperatures dropped by several degrees and ice sheets covered much of North America and Northern Europe. The oscillations are not smooth or symmetrical. The transitions into glacial periods are gradual, taking tens of thousands of years, while the transitions out of them are abrupt, sometimes occurring over just a few thousand years. The pattern is often described as a sawtooth, with long, slow descents into cold and rapid climbs back to warmth, and the sawtooth repeats with a dominant period of about 100,000 years, paced by the eccentricity cycle. Within each major cycle, smaller variations appear at the 41,000 year and 23,000 year periods, reflecting the influence of obliquity and precession. The record is a testament to the power of small changes in the distribution of sunlight to tip a complex system between stable states, and it is also a testament to the fact that even a stable obliquity range does not prevent dramatic climate shifts. The Moon holds the axis steady, but steady does not mean static, and the climate has been anything but static. What the Milankovitch framework makes clear is that Earth's climate is sensitive to variations in the geometry of its motion, and that the variations the planet currently experiences are small. The obliquity cycle in particular is narrow, a swing of just over 2 degrees, from 22.1 to 24.5, over 41,000 years. That swing is enough to influence the advance and retreat of ice sheets, but it is not enough to fundamentally reorganize the climate system. The poles remain cold, the tropics remain warm, and the gradient between them remains steepy enough to drive the atmospheric circulation patterns that distribute heat and moisture around the planet. The seasons remain recognizable, predictable, and the life that evolved in those seasons has had time to adapt to the variations within them. The obliquity cycle is one of the variables that the Moon constrains, and the constraint is the reason the cycle is so narrow. Without the Moon, the obliquity would not oscillate within a 2-degree range over 41,000 years. It would wander, over millions of years, across a range 10 or 20 times larger, and the climate system would be forced to respond not to small cyclical nudges, but to large chaotic lurches. The Ice Age cycles would still exist, in the sense that eccentricity and precession would still vary, but they would be superimposed on a much larger and less predictable variation in obliquity, and the result would be a climate record that looked less like a sawtooth and more like noise. The Milankovitch cycles are orderly because the obliquity is stable, and the obliquity is stable because the moon is there. The connection between the moon and the ice ages is indirect, mediated by the axial tilt, but it is real, and it is part of the larger story of how the moon has shaped the conditions under which complex life evolved on Earth. The realization that the moon is receding, and that its recession is weakening the stabilization it provides, introduces a new dimension to the story. The recession is not a recent discovery. It was inferred in the 19th century from the slowing of Earth's rotation, and it was measured directly in the 1970s using the retroreflectors left on the lunar surface by the Apollo astronauts and the Soviet Lunokhod rovers. The measurements are made by firing laser pulses at the retroreflectors and timing the return signal, and the precision of the technique is now such that the distance to the moon can be determined to within a few millimeters. The current rate of recession is 3.8 centimeters per year, which is small enough that it would take more than 25,000 years for the moon to recede by a single kilometer. But it is also relentless, and over geological time the cumulative effect is large. The moon is now about 384,000 kilometers away, and it was much closer in the past. 4.5 billion years ago when it formed, it orbited at a distance of perhaps 15,000 to 25,000 kilometers, and the tides it raised on the early Earth were enormous, strong enough to dissipate energy at a rate that drove the moon outward relatively quickly at first, and then more slowly as the distance increased and the tidal forces weakened. The recession has been ongoing ever since, powered by the transfer of angular momentum from Earth's rotation to the moon's orbit, and the process is still happening now, at a rate that can be measured with lasers fired from observatories in New Mexico and Texas and France. The rate itself is not a simple clock that can be projected forward or backward with confidence. If it were, and if the moon had been receding at 3.8 centimeters per year for its entire history, then it would have been in contact with Earth just 1.5 billion years ago, which is far too recent given that the moon is known to be about 4.5 billion years old. The discrepancy arises because the recession rate is not constant. It depends on the rate at which tidal energy is dissipated, and the dissipation rate depends on the configuration of Earth's oceans and continents, which change over geological time as the plates move and the ocean basins open and close. The current rate is anomalously high, elevated by a tidal resonance in the North Atlantic, which accounts for about 41% of the global tidal energy dissipation. When the continents were arranged differently, and the ocean basins had different shapes, the resonance conditions were different, and the dissipation rate was lower. Geological evidence from rhythmically layered sediments, such as those found in Western Australia, suggest that the average recession rate over the last 2.5 billion years has been closer to 1.2 centimeters per year, which is less than a third of the current rate. The implication is that the future of the moon's orbit cannot be predicted simply by extrapolating the present rate forward. The dissipation rate will change as the continents continue to drift, and the resonances that currently amplify the tides will shift or disappear. The direction of the recession is certain, but its speed is not, and any projection into the deep future must account for the fact that the tidal system is sensitive to factors that are themselves evolving and uncertain. What can be said with confidence is that the moon will continue to recede, that the tidal forces will continue to weaken, and that Earth's rotation will continue to slow as angular momentum is transferred to the lunar orbit. The lengthening of the day is small by human standards, about 1 to 2 milliseconds per century, but over geological time it adds up, and the day that was once 4 to 6 hours long in the immediate aftermath of the moon's formation is now 24 hours, and it will be longer still in the future. The slowing of the rotation has a direct effect on the precession of the spin axis, because the precession rate depends on the rate at which the planet is spinning. A slower rotation means a slower precession, and a slower precession means that the frequency of the precessional motion drops closer to the frequencies of the orbital perturbations caused by the other planets. The concern is that when the frequencies become close enough, the system can enter a resonance, and when it does, the obliquity can begin to grow. The growth is not immediate and not necessarily rapid, but it is cumulative, and once it begins, the system can cross a threshold beyond which the obliquity no longer oscillates within a narrow range but wanders chaotically across a much larger one. The timing of the resonance crossing is uncertain, because it depends on the future evolution of the tidal dissipation rate, which is uncertain, and on the details of the planetary orbits, which are themselves subject to chaotic variations over very long timescales. But the basic mechanism is well understood, and the question is not whether the resonance will eventually be encountered, but when. The model suggests that the stability will persist for tens of millions of years at least, possibly as long as a few hundred million, depending on how quickly the precession slows and how the tidal system evolves. The uncertainty is large, because the models are sensitive to parameters that are difficult to constrain, and because the system is chaotic in the technical sense, meaning that small differences in initial conditions can lead to large differences in outcome over long timescales. But the range of estimates, while broad, is bounded, and all of them point to the same conclusion. The present arrangement, in which the Moon holds the obliquity within a narrow range and the climate responds to small predictable orbital cycles, is not a permanent feature of the planet. It is a feature of this particular epoch in Earth's history, an epoch that sits in the middle of a much longer trajectory from the Moon's formation to its eventual departure into a wider, more distant orbit. The stability is real, but it is conditional, and the condition is a gravitational coupling that weakens with every passing year. The Moon recedes at 3.8 centimeters per year, and each centimeter represents a small reduction in the torque it exerts on Earth's equatorial bulge, and each reduction in torque corresponds to a small slowing of the precession, and the slowing is cumulative, and the cumulative effect is that the precession frequency is drifting downward slowly but inexorably toward the frequencies that spell instability. The awareness of this trajectory is recent, in the sense that it emerged from computational models that were not possible until the late 20th century, but the trajectory itself has been unfolding for billions of years. The Moon has been receding since it formed, and the axial stability it provided has been weakening since it formed, and the climate system has been responding to the weakening in ways that are difficult to disentangle from the other factors that drive climate change over geological time. The planet's climate has been shaped by volcanism, by the drift of continents, by the evolution of life and the changing composition of the atmosphere, by impacts and ocean circulation and 100 other variables, and the role of axial stability is just one thread in a very complex tapestry. But it is a thread that runs through the entire history of the planet, and it is a thread that will eventually break, not suddenly but gradually, as the precession slows and the resonances approach, and the obliquity begins to wander beyond the narrow corridor it has occupied for billions of years. When that happens, the climate system will lose one of the constraints that has shaped it since the Moon formed, and the loss will not be irreversible, because the Moon will not return, and the torque will not increase, and the precession will not speed up again. The dynamical state of the planet will have shifted, and the shift will be permanent, or at least as permanent as anything on a planet that is itself temporary. The comparison to Mars is instructive here, because Mars is what Earth might have been without the Moon, or what Earth will eventually become when the Moon's influence fades. Mars has two small moons, Phobos and Deimos, but they are too small to stabilize its axis, and its obliquity has wandered over a large range, probably from near zero to more than 60 degrees, over the last few tens of millions of years. The climate record on Mars is one of chronic instability, with ice deposits that migrate from pole to pole, atmospheric pressure that varies by factors of several, and surface conditions that oscillate between states that are cold and dry, and states that are even colder and even drier. The planet has never settled into a stable climate, and the lack of stability is one of the reasons it lost much of its atmosphere and surface water over geological time. The contrast with Earth could not be sharper, and the contrast is largely attributable to the Moon. Earth has had a stable obliquity for billions of years, and the stability has allowed the climate to vary within bounds that are narrow enough for life to adapt, and for ecosystems to evolve, and for the slow processes of weathering and sedimentation and plate tectonics to maintain a surface environment that, while far from static, has been predictable enough that the long experiment of biological evolution could unfold without being repeatedly reset by chaotic swings in axial tilt. The stability is a gift, but it is a temporary gift, and the awareness of its temporariness is part of the larger awareness that the conditions that made Earth habitable are not universal properties of terrestrial planets, but contingent outcomes of specific histories and specific accidents. The accident that gave Earth its moon was a collision, the same collision that destroyed the primordial planet and created the planet we live on now, and the collision also gave the planet the axial stability that has characterized it ever since. The stability is now eroding, not because of any new event, but because the moon is doing what moons do, receding under the influence of tidal forces, slowly and inexorably, until it reaches a distance at which the tidal coupling is too weak to hold the axis steady. The erosion is slow enough that it will not matter to anything alive now, or to anything that will be alive for thousands of generations, but it is happening, and it is measurable, and it is irreversible. The corridor of stability is narrowing year by year, centimetre by centimetre, and the resonances that will destabilise the axis are embedded in the orbital architecture of the solar system, waiting. They are not external threats. They are not contingent on anything that might or might not happen. They are already there, built into the gravitational relationships among the planets, and the only reason they have not yet destabilised Earth's obliquity is that the precession has been fast enough to avoid them. The precession is slowing, and the avoidance will not last indefinitely, and when it ends, the planet's climate will enter a regime that it has not experienced since before the moon formed. A regime characterised not by cyclical variations around a stable mean, but by chaotic swings between extremes. The timescale is long enough that it is difficult to grasp, and the changes will unfold so slowly that no generation will perceive them as a crisis, but the endpoint is clear. Earth's present climate stability is not a permanent attribute of the planet. It is a temporary dynamical state, maintained by a gravitational coupling that is weakening and that will eventually fail. The failure is not a matter of speculation. It is a consequence of known physics acting on a system whose behaviour is increasingly well understood, and the only uncertainty is in the timing, not in the outcome. The planet we live on is stable because of the moon, and the moon is leaving, and the leaving is not a metaphor. It is a process that can be measured with lasers, tracked in the changing length of the day, and projected into a future in which the axis will eventually break free of the constraint that has held it for billions of years. The breaking free will not happen tomorrow, or in 10,000 years, or even in 1,000,000, but it will happen, and when it does, the history of Earth's climate will have crossed a threshold from which there is no return. The seasons will begin to swing, the climate will lose its predictability, and the planet will become, in a very real sense, a different world. The world we know, the world of stable seasons and cyclical ice ages, and a climate that varies but remains within bounds, is the world of the moon's influence, and the influence is fading. What comes after is not unknowable, but it is uncertain, and the uncertainty is built into the nature of chaos itself. The models can show the boundaries of the possible, but they cannot predict the exact trajectory, because the trajectory depends on initial conditions that cannot be known with infinite precision, and on perturbations that will accumulate over time scales too long to simulate in full detail. What is known is that the stable state will give way to an unstable one, and that the transition, once begun, will not reverse, and that the default state for a terrestrial planet is not stability, but chaos. Earth has been an exception, held out of the chaotic regime by a companion that formed in a collision and that is now slowly drifting away into the dark. The question then is when? Not whether the axis will break free, that is settled, but when the precession will slow enough that the resonances can take hold, and when the first chaotic swings will begin to appear in the obliquity record, and how long the transition from bounded variation to unbounded wandering will take. The answer depends on details that are difficult to pin down with precision. The future distribution of continents and ocean basins, which will change the efficiency of tidal dissipation. The future rate of the moon's recession, which is not a constant over geological time, and the exact frequencies of the planetary perturbations, which shift subtly as the orbits of Venus, Jupiter and the other planets evolve. But the broad time scale is known, and it is long. The models suggest that Earth's axial stability will persist for tens of millions of years at minimum, and possibly for more than 100 million, before the precession slows enough to allow resonance. Some estimates place the threshold further out still, beyond several 100 million years, though those estimates depend on assumptions about the moon's future recession rate that are themselves uncertain. What is not uncertain is that the threshold exists, and that it lies somewhere in the deep future, and that crossing it will mark the end of the climate regime that has prevailed for the entire span of recorded geological history. The transition will not be abrupt. The axis will not suddenly lurch from 23 degrees to 60 degrees in the span of a single orbit, or even in the span of 1,000 orbits. The destabilization will unfold over millions of years as the precession frequency drifts into the resonance zone and the obliquity begins to wander beyond the bounds it has observed for so long. At first, the wandering will be small, a few degrees beyond the current range, and the climate effects will be correspondingly modest, indistinguishable perhaps from the natural variability that already exists. But the wandering will grow, and the swings will become larger, and eventually the obliquity will reach values that have no precedent in the climate history that geologists have reconstructed from ice cores and sediment layers and fossil pollen. The planet will experience summers in which the poles receive more sunlight than the equator, and winters in which the high latitudes are plunged into months of uninterrupted darkness, and the ice sheets will advance and retreat in patterns that no longer follow the predictable rhythms of the Milankovitch cycles. The biosphere will adapt, as it always has, but the adaptations will be harder, and the margins narrower, and the intervals between stable states shorter, and the question of what constitutes a stable state will become increasingly difficult to answer. Mars offers a preview of what that regime looks like, though Mars is an imperfect analogue, smaller and colder and lacking the thick atmosphere that Earth retains. The Martian obliquity has varied over a range of at least 45 degrees, and possibly as much as 80, over the past 10 million years, driven by the same planetary resonances that will eventually destabilize Earth, but unmoderated by the torque of a large moon. The swings have been chaotic in the technical sense, sensitive to initial conditions, unpredictable in detail, governed by equations that have no closed-form solution. When the obliquity is low, near 0 degrees, the poles are the coldest places on the planet, colder than the equator by hundreds of degrees, and the carbon dioxide in the thin Martian atmosphere condenses out at the poles as dry ice, leaving the air even thinner. When the obliquity is high, near 60 or 70 degrees, the poles receive more annual sunlight than the equator, and the dry ice sublimates, and the atmospheric pressure rises, and the climate reorganizes itself around a new distribution of heat and cold. The planet does not settle into a new equilibrium. It lurches from one transient state to another, and the time it spends in any given state is shorter than the time it takes for the surface to adjust fully to the new conditions. The result is a climate that is never in balance, never predictable, never stable in the way that Earth's climate has been stable. Earth will not become Mars. The atmosphere is thicker, the gravity stronger, the distance from the sun closer, and the details of the climate system are different in ways that matter. But the underlying dynamics are the same, and the outcome in broad terms is likely to be similar. a planet whose axial tilt wanders chaotically, whose seasons lose their regularity, whose climate zones shift faster than ecosystems can migrate, and whose long-term habitability becomes contingent on factors that are difficult to predict and impossible to control. The transition will not render the planet uninhabitable in any absolute sense. Life has survived far worse disruptions, including the snowball Earth episodes of the Proterozoic, in which the entire surface was frozen for millions of years. But it will end the relatively benign climate regime that has prevailed since the Moon's stabilizing influence took hold, and it will replace that regime with something far less forgiving. The timescale is long enough that it invites a kind of abstraction, a sense that the distant future is not quite real, or not quite relevant, or not quite connected to the present in any way that demands attention. But the connection is there, and it is direct, and it runs through the same physical processes that govern the present climate. The tides that are currently pushing the Moon away from Earth are the same tides that will eventually slow the precession enough to allow resonance. The resonances that will destabilize the obliquity are the same resonances that are acting on the planet now, held at bay only by the precession that the Moon induces. The future is not separate from the present. It is the continuation of the present, played forward through time according to the laws of motion and gravitation, and the outcome is not mysterious. It is the logical consequence of a system whose initial conditions were set 4.5 billion years ago, when a Mars-sized protoplanet collided with the early Earth and threw enough debris into orbit to form the Moon. The collision was not, in any sense, designed to produce a stable climate. It was a catastrophe, the near-total destruction of the planet that existed before the impact, and the Moon was a byproduct, not a purpose. The stability that followed was an accident, the result of the Moon happening to be large enough and close enough to exert a torque on the Earth's equatorial bulge, and the torque happening to be strong enough to keep the precession fast enough to avoid resonance. There is no reason to expect that such an arrangement would arise naturally, and no reason to expect that it would persist indefinitely once it did arise, and no reason to interpret the stability as anything other than what it is, a temporary dynamical state, contingent on a gravitational coupling that is weakening. The fact that the state has persisted for billions of years does not make it permanent. It makes it long-lived, which is not the same thing. Other terrestrial planets in the solar system did not acquire large moons, and their axial tilts are correspondingly unstable. Venus, with no moon at all, rotates so slowly that its axial precession is dominated by the Sun's gravitational torque rather than by its own rotation, and its obliquity has likely been chaotic over its history, though the details are obscured by the planet's thick atmosphere and lack of a preserved geological record. Mercury, also moonless, has a very low obliquity, close to 0 degrees, but that configuration is not stable. It is the result of tidal locking with the Sun, which has damped out any axial variations that might once have existed. Mars, as noted, has 2 tiny moons, Phobos and Deimos, but their combined mass is less than a 10,000th of Earth's moon, and they exert no meaningful torque on the Martian axis. The result is that Mars's obliquity has wandered across a wide range, and the planet's climate has been correspondingly unstable, and the instability has likely contributed to the loss of the planet's atmosphere and the desiccation of its surface. Earth, by contrast, has had a large moon for most of its history, and the Moon has kept the axis stable, and the stability has allowed the climate to vary within bounds, and the bounded variation has made it possible for complex life to evolve and persist. The causal chain is not ironclad. There are other factors that contribute to habitability, including the planet's distance from the Sun, the strength of its magnetic field, the composition of its atmosphere, and the presence of liquid water. But the axial stability is part of the chain, and it is a part that depends entirely on the Moon. The Moon, then, is not merely a companion, or a light in the night sky, or a driver of tides. It is a stabilizer, and the stability it provides is one of the conditions that have made Earth a habitable planet. The fact that the stability is temporary does not diminish its importance. It simply places Earth's habitability in a longer context, one in which the present is a phase rather than a permanent state, and the future is something different. The phase has lasted for billions of years, which is a very long time by any human measure, and a significant fraction of the age of the planet itself, but it is not infinite, and it is not the endpoint of Earth's climate history. The endpoint, if there is one, lies much further in the future, beyond the threshold at which the axis begins to wander, and beyond the point at which the sun's gradual brightening renders the surface too hot for liquid water, and beyond the eventual expansion of the sun into a red giant, which will occur in roughly 5 billion years and will likely engulf the inner planets entirely. But long before any of that, the moon's recession will have weakened the gravitational coupling enough to allow resonance, and the axis will have begun to swing, and the climate will have entered the chaotic regime. The prospect of that regime raises a question that is difficult to answer: whether a large moon is a requirement for habitability or merely an advantage. The question matters because it bears on the likelihood of finding habitable planets elsewhere in the galaxy, and on the conditions that such planets would need to satisfy. If a large moon is necessary, then habitable planets are likely to be rare, because large moons are thought to be rare, and the circumstances that lead to their formation, giant impacts at just the right angle, with just the right mass ratio, occurring at just the right time in a planet's history, are correspondingly uncommon. If a large moon is merely an advantage, then habitability may be more widespread, though planets without large moons would be expected to have less stable climates and shorter habitability windows. The question is not yet settled. Some planetary scientists argue that a large moon is essential, pointing to Earth's example and to the chaotic climates of moonless or nearly moonless planets in the solar system. Others argue that the requirement is overstated, pointing to the fact that Earth's obliquity, even without the moon, would not wander instantaneously, and that a planet with a faster rotation rate or a different orbital configuration might remain stable even without a large moon. A study published in 2015 used modern supercomputing to re-examine the question, and found that a moonless Earth, under certain assumptions, might experience obliquity variations of only 10 degrees or so beyond the current range, rather than the 60-degree swings predicted by earlier models. The discrepancy arises from differences in the assumptions about Earth's rotation rate and the details of the resonance interactions, and it illustrates the difficulty of making confident predictions about systems whose behavior is sensitive to initial conditions. But even the more optimistic models do not suggest that a moonless Earth would be as stable as the Earth we have. They suggest only that it might be somewhat more stable than Mars, which is a low bar. The debate is unlikely to be resolved by studying Earth alone, because Earth has only one history, and that history includes the Moon. The resolution, if it comes, will come from studying exoplanets, the planets orbiting other stars, and from determining how many of them have large moons, and how many of them show signs of stable climates despite lacking such moons. The detection of exomoons, moons orbiting exoplanets, is currently at the edge of observational capability, and only a handful of candidate exomoons have been identified, none of them confirmed. But the techniques are improving, and within the next few decades it may become possible to survey a large sample of exoplanets and determine what fraction of them have moons comparable in size to Earth's moon, and whether those planets show any correlation between the presence of a large moon and the stability of their climates. Until then, the question remains open, and the moon's role in Earth's habitability remains a case study, suggestive but not definitive. What is definitive is that the moon has played that role for Earth, and that the role is ending, and that the ending is not a matter of choice or intervention but of physics. The same tidal forces that have kept the Earth-Moon system evolving for 4.5 billion years will continue to act, and the moon will continue to recede, and the precession will continue to slow, and the resonances will continue to wait. The threshold will be crossed, eventually, and the axis will begin to wander, and the climate will lose the predictability that it has maintained for as long as there has been a moon to maintain it. The fact that the threshold lies tens or hundreds of millions of years in the future does not make it irrelevant. It makes it remote, but remoteness is not the same as irrelevance, and the processes that will carry the planet across that threshold are already underway, measurable in the present, encoded in the recession rate and the lengthening day and the changing tides. And the measurement continues night after night at the laser ranging station in the Sacramento Mountains of New Mexico, where the green pulses climb through the atmosphere and make the 238,000-mile crossing to the lunar surface and reflect off the retroreflector arrays left by the Apollo astronauts and the Soviet rovers more than 50 years ago. The round trip takes between 2¼ and 2¾ seconds, depending on where the moon is in its elliptical orbit, and the return signal is faint. Just a handful of photons out of the trillions that were sent, but it is enough. The photons are collected by the telescope, their arrival times recorded to within billionths of a second, and the distance is calculated to within a few millimeters, and the data are logged and archived and added to the decades-long record that has been accumulating since the first successful ranging measurement was made in the summer of 1969. The record shows, unambiguously, that the moon is receding at an average rate of 3.8 centimeters per year, though the rate varies slightly from year to year, modulated by the 18.6-year lunar nodal cycle and by longer-term changes in the distribution of tidal dissipation across the ocean basins. The precision is extraordinary, the result of decades of incremental improvements in laser technology and timing systems and atmospheric correction algorithms. And the record is now long enough to detect not just the recession, but the variations in the recession, and to begin to constrain the models of tidal dissipation that govern the rate at which angular momentum is transferred from the Earth's rotation to the Moon's orbit. The people who operate the ranging station are not thinking most nights about the distant future in which the axis will break free. They are thinking about the immediate tasks, aligning the telescope, compensating for atmospheric turbulence, tracking the moon as it moves across the sky, verifying that the return signal is clean and that the timing data are accurate. The work is technical, meticulous, and repetitive, and it requires a kind of patience that is difficult to sustain over years and decades, but it is the only way to measure the recession with the precision that the science requires. The ranging station is not the only one in the world. There are similar facilities in France and Germany and Australia, part of a loose international network that shares data and coordinates observations, but the station at Apache Point, perched at an altitude of more than 9,000 feet above the desert floor, has some of the clearest skies and the most sensitive equipment, and it has contributed a disproportionate share of the measurements that define the current recession rate. The station is small, the staff smaller, and the work receives little attention outside the narrow community of scientists who study Earth's rotation and the dynamics of the Earth-Moon system. But the measurements it produces are among the most precise in all of observational astronomy, and they are the foundation for understanding a process that will shape the planet's climate for hundreds of millions of years to come. The retroreflectors themselves, sitting on the lunar surface, require no maintenance and no power. They are passive devices, corner cubes of fused silica, arranged in arrays and mounted on panels that were carefully leveled by the astronauts who placed them. The largest array, left by the Apollo 15 mission in 1971, measures 105 centimeters by 65 centimeters and contains 300 corner cubes. The smaller arrays, left by Apollo 11 and Apollo 14, have fewer cubes and are correspondingly dimmer, but all of them are still functional, still reflecting photons back toward Earth, with the same efficiency they had when they were new. The Soviet Lunokhod rovers, which carried their own retroreflector arrays, landed in different locations and provide additional ranging targets, though they are used less frequently because their positions are less precisely known. The arrays have been sitting on the moon for more than 5 decades now, exposed to the vacuum and the temperature extremes, and the micrometeorite impacts, and the ultraviolet radiation that bathes the lunar surface, and they show no signs of degradation. They are, in a sense, the most durable scientific instruments ever built, and they will likely remain functional for centuries or millennia, long after the space programs that place them have been forgotten. The measurements they enable are not merely scientific curiosities. They are records of a process that connects the present to the deep past and the distant future. A process that began when the moon formed, and that will continue until the Earth and moon reach a final equilibrium, billions of years from now, in which both bodies are tidally locked to each other, presenting the same face to each other at all times, and the day and the month are the same length. That equilibrium will never actually be reached because the sun will evolve into a red giant first, and the dynamics of the system will be altered beyond recognition, but the trajectory toward equilibrium is nonetheless real, and it is the trajectory that the ranging measurements are tracking. The moon's recession is not a deviation from some ideal state. It is the continuation of the process that has governed the Earth-Moon system since the moment of its formation, and the recession will continue at whatever rate the tides and the ocean basins and the gravitational perturbations dictate, until some external event intervenes or the system reaches its endpoint. The measurements are a way of watching the future arrive slowly and inexorably in the present, and the future that is arriving is one in which the moon's influence on Earth is diminishing year by year, centimetre by centimetre, and the stability that the moon has provided is correspondingly weakening. The weakening is not yet significant. The precession is still fast enough to avoid resonance. The obliquity is still confined to its narrow range. The climate is still predictable in the sense that it varies according to known cycles. But the weakening is real, and it is cumulative, and it is irreversible. The moon's recession is driven by the dissipation of tidal energy, and the dissipation is driven by friction in the ocean basins, and the friction is a consequence of the fact that the ocean basins are shallow and irregularly shaped, and filled with water that cannot flow freely in response to the tidal forces. The energy dissipated as heat comes from the Earth's rotation, which slows as the tidal bulge lags behind the moon's orbital motion, and the angular momentum lost by the Earth is gained by the moon, which moves into a higher, slower orbit. The process is continuous, gradual and unidirectional, and it will continue as long as there are tides, which is to say, as long as the moon is close enough to raise tides and the Earth is spinning fast enough to create a tidal lag. The system is evolving, and the evolution is carrying it toward a configuration in which the gravitational coupling is weaker, and the stability is correspondingly reduced, and the axis is more vulnerable to perturbation. The perturbations are not hypothetical. They are present in the system now, embedded in the orbits of the other planets, expressed as slow oscillations in the orientation of Earth's orbit relative to the fixed stars. The oscillations have periods of tens of thousands to hundreds of thousands of years, and they are caused by the gravitational interactions among all the bodies in the solar system, weighted by their masses and distances. Jupiter, because it is the most massive planet, contributes the largest perturbations, but Venus and Mars and the other planets contribute as well, and the perturbations add up in ways that depend on the exact configuration of the orbits at any given time. The perturbations are not strong enough by themselves to change Earth's obliquity by more than a small amount, because the precession of the equinoxes, driven by the moon's torque, keeps cycling the orientation of the axis faster than the perturbations can build up. The precession in effect averages out the perturbations over time, preventing any one of them from locking onto the axis and driving it into resonance. But the averaging works only as long as the precession is fast enough and the precession is slowing, and when it slows enough that its period becomes comparable to the period of one of the perturbations, the averaging will fail, and the perturbation will begin to amplify rather than cancel, and the obliquity will begin to wander. The transition from bounded variation to chaotic wandering will not be sudden, but it will be irreversible, and it will mark the end of the climate regime that has prevailed since the moon formed. The moon, then, is not a guarantor of stability. It is a source of temporary stability, and the temporariness is built into the system's dynamics. The stability has lasted for billions of years, which is long enough to encompass the entire history of complex life on Earth, and long enough to seem, from a human perspective, almost infinite, but it is not infinite, and it will not last indefinitely, and the processes that will end it are already in motion. The moon's recession is not a countdown to catastrophe. The timescale is too long for that. But it is a countdown to transition, a transition from one dynamical regime to another, and the transition is as certain as the laws of motion and gravitation can make anything. The planet we live on is the product of its history, and its history includes the collision that formed the moon, and the moon's influence on the axis, and the axis's influence on the climate, and the climate's influence on the evolution and distribution of life. All of those influences are connected, and all of them are changing, and the changes are carrying the planet toward a future that is fundamentally different from the present. The difference is not that the future will be inhospitable. Earth has been inhospitable before, during the snowball episodes and the mass extinctions and the long eons before oxygen appeared in the atmosphere. But that the future will be less predictable. The climate will lose the regular variations that have characterized it for so long, and the loss of regularity will make adaptation harder, and the margins for survival narrower, and the question of what constitutes a stable environment more difficult to answer. The transition will unfold over millions of years, which is too long for any individual organism or species or ecosystem to experience. But it is not too long for the planet as a whole, and it is not too long for the geological record, and it is not too long for the models to anticipate. The future is not unknowable, it is uncertain in detail, but clear in outline, and the outline is one in which the moon's influence fades, and the axis breaks free, and the climate enters a new regime, and the planet becomes, in a very real sense, a different world. The laser pulses climbing through the night sky from the Sacramento Mountains are measuring that process, one photon at a time, and the measurements are accumulating into a record that future generations will interpret as the beginning of the end of the stability that the moon provided. The stability was never guaranteed, and it was never meant to last forever, and the fact that it is an ending is not a failure of the planet or of the moon, but simply the continuation of the dynamics that have governed the Earth-Moon system since its formation. The moon is leaving, not because it wants to or because it is being driven away by some external force, but because it is following the trajectory that the laws of physics prescribe, and the trajectory leads away from the Earth, slowly and inexorably, into a future in which its influence is diminished, and its role as a stabilizer is ended. The ending is not an event, it is a process, and the process is already underway, and the measurements from the ranging station are the proof that it is real, and that it is happening, and that it is irreversible. The moon's departure is a gift of gravity, given and then slowly withdrawn, and what remains when the gift is gone is a planet more typical of its kind. A spinning world in a gravitational crowd, unmoored, vulnerable, its axis free to wander according to the perturbations that have always been there, waiting for the moment when the stabilizer is no longer strong enough to hold them at bay.